Welcome to tonight's journey of science to sleep by, where science becomes a lullaby for your mind. Tonight, we'll explore one of the deepest mysteries of the cosmos, a question that reaches back to the very first moments after the Big Bang. Why did the universe choose matter over antimatter? If matter and antimatter were born in equal amounts, why are we here at all? Why is there something, instead of nothing? Together, let's slow down, breathe, and let the mystery unfold like a cosmic bedtime story. To begin this journey, imagine yourself at the very start of time, before stars, before planets, before the quiet rhythm of galaxies drifting in the cosmic sea. The universe, as science tells us, began with an explosion of pure potential, what we now call the Big Bang. In that instant, matter and antimatter were born together, as if the universe was painting with two brushes, creating particles of substance and their mirror opposites in equal measure. For every particle of matter, there was a twin of antimatter, identical in mass, yet opposite in charge. This perfect balance should have meant that one day, they would meet, collide, and vanish back into light, erasing themselves in flashes of pure energy. And yet, here we are. Stars shine above us, the earth spins quietly below, and life breathes in the silence of night. Something tipped the scales. Something about the universe chose matter over antimatter, ever so slightly, but just enough to allow all of existence to take root. When scientists look at this puzzle, they begin with the idea of balance. Balance is the natural order we expect to see in physics. If two things are created together, in equal and opposite ways, we expect them to cancel. Matter and antimatter follow this rule with astonishing precision. When a particle of matter meets its opposite, they annihilate completely, leaving nothing behind but a burst of energy. This is not like the collisions we are familiar with on Earth, where two objects break apart or scatter. This is total destruction of both, a vanishing act that leaves only light as the reminder. If everything had followed this script, if the universe had kept that perfect balance, then after the Big Bang, there should have been only radiation. No atoms, no molecules, no galaxies gathering into spirals, no stars burning in their cores, and certainly no people gazing upward in wonder. The very fact that matter survived is the first clue that the early universe did not play fair. Scientists often describe it in terms of a tiny excess. Imagine a billion particles of matter, paired with a billion particles of antimatter. They meet, they annihilate, they dissolve into flashes of photons. But in this vast crowd, there is one extra particle of matter left over. That single survivor becomes the seed of reality. Now multiply that imbalance across the entire cosmos, and suddenly, those 1 in a billion leftovers become enough to form stars, enough to gather into galaxies, enough to build the scaffolding of everything we know. It is humbling to realize that the existence of our world, and the very fact that you are listening to this quiet reflection, is built upon a sliver of imbalance so small, it is almost impossible to imagine. The Big Bang produced near perfection, yet that tiny imperfection changed everything. When we think about balance, we often think of it as a calm and steady state. But here, balance was dangerous. If the scales had been truly even, the universe would have been cold, sterile light. Instead, the early universe was a place where the rules bent just enough. In that first fraction of a second, quarks and antiquarks, electrons and positrons, neutrinos and antineutrinos, all danced in a dense, hot plasma. They collided, they destroyed one another, they re-emerged again from the surrounding energy. It was chaos, a storm of creation and destruction happening faster than human senses can comprehend. And yet, when the storm calmed, matter had managed to cling on, like a faint echo that refused to be silenced. In physics, we often describe this story as symmetry and its breaking. Symmetry is the idea that nature treats opposites equally, that the laws governing one side mirror the laws governing the other. But in the case of matter and antimatter, the symmetry did not hold perfectly. Somewhere, hidden in the laws of the universe, there was a preference. This preference was not obvious, not large, but small enough to tip the outcome. To scientists, this imbalance is both a mystery and a gift. Without it, we would not be here to ask the question. With it, We live in a universe of substance, of mountains and rivers, of stars and galaxies, of quiet nights where we can wonder why it all came to be. It is tempting to see this choice, this preference, as something intentional, as if the universe itself decided to lean toward matter. But in science, it is not about choice in a human sense. It is about laws and patterns, written into the structure of reality itself. When the Big Bang unfolded, the mathematics of physics gave us outcomes, and one of those outcomes was this astonishing imbalance. The story of matter's survival is not only the story of particles and annihilation, it is the story of why there is something rather than nothing, why existence triumphed over void. As we reflect on this, imagine the calm of deep time. Nearly 14 billion years have passed since that beginning. The faint glow of the Big Bang, what we call the cosmic microwave background, still shines in the sky, stretched and cooled by the expansion of space. It is a whisper from those first moments, a reminder of the balance that almost canceled everything out. And yet, from that whisper, the universe grew. From that tiny remainder of matter, stars formed, heavy elements were forged, planets coalesced, and life began its long journey. For many scientists, the question of why matter survived is not just a technical puzzle, but a doorway into understanding the deeper structure of the cosmos. It is a reminder that even the smallest details matter. A 1 in a billion difference became the foundation of galaxies. A slight tilt in the cosmic scales became the reason for every breath you take. If the universe had leaned the other way, we would not be here to notice. The Big Bang gave us a universe of near perfection, but it is imperfection that gave us life. In the quiet of night, when the stars above feel timeless and unchanging, it is worth remembering that they too are products of that imbalance. Each point of light you see is a monument to the moment matter won its fragile victory over Antimatter. Each star is a survivor, built from the leftover particles that endured the annihilation. Even the atoms in your body, carbon, oxygen, iron, all trace their existence back to that same event. The universe chose matter, and in doing so, it chose us, though not in any conscious sense, but in the deep unfolding of physical laws. And so, the balance of the Big Bang remains both a mystery and a gift. It is the reason the night sky is not empty, the reason we can dream, and the reason we can ask questions about the origin of everything. The fact that matter survived is the reason stories can be told, songs can be sung, and journeys can unfold across the cosmos. The story of matter and antimatter is not just about creation. It is also about destruction, an endless cycle written into the fabric of the universe itself. To understand why the universe is filled with stars and galaxies instead of pure light, we must first understand the dance of annihilation. It is a dance unlike anything we see in our daily lives. When matter and antimatter meet, there is no clash that leaves debris behind, no fragments scattered across the floor of reality. Instead, they embrace, and in that embrace, they vanish. Every ounce of their mass is transformed into energy, a perfect conversion, leaving behind no particle at all, only a burst of radiation traveling outward into space. This process is not violent in the way we often imagine explosions. It is precise, absolute, and inevitable. It is the great eraser of existence, and yet, from within it, we learn how delicate the survival of matter truly was. When we speak of annihilation, the word itself carries a kind of finality. To annihilate is to reduce something to nothing, to wipe away its presence so completely that no trace remains. This is exactly what happens when a particle of matter encounters its antimatter twin. Imagine an electron, tiny speck carrying a negative charge, orbiting within an atom. Now imagine its antimatter counterpart, the positron, carrying a positive charge, but otherwise identical in mass. If these two ever meet, they do not repel, they do not bounce away. They meet in a perfect moment of cancellation, releasing their combined mass as photons, as light, as energy itself. It is a process that follows the deepest rules of physics, the law of conservation of energy, yet it feels almost poetic in its completeness. Something tangible, something real, vanishes into something intangible, a ripple of energy moving outward into the infinite dot in the early universe. Just after the Big Bang, annihilation was not a rare occurrence. It was the rhythm of existence. Particles and antiparticles filled the newborn cosmos in unimaginable numbers. They collided constantly in the hot, dense plasma, each encounter releasing light into the sea of energy already flooding space. This dance went on ceaselessly, a balance of creation and destruction, of substance turning into radiation, and radiation turning back into substance. The universe was a grand laboratory, running this experiment on the largest possible scale. For every moment of survival, there was an equal moment of erasure. If one looked at the scene, it might have appeared hopeless for matter to endure, because every advantage it had seemed to be erased as quickly as it appeared. To imagine this more closely, think of a vast ballroom filled with dancers, each paired perfectly with a partner. Every step forward brings them into each other's arms, and with each embrace, they disappear from the floor, replaced by the faint shimmer of light drifting across the room. The dance floor grows emptier, the music echoes into the void, and one might believe that eventually no dancers would remain. And yet, somehow, a few linger at the edges, never quite erased, never quite drawn fully into the annihilation. These survivors become the building blocks of everything that follows. That is the nature of the annihilation dance. It is absolute in principle, but imperfect in practice, and that imperfection is why we are here to reflect on it. What makes this process so striking is its efficiency. In the collisions we know from our world, such as two cars crashing, the energy is spread into many forms: heat, sound, broken fragments. Nothing disappears entirely. But in matter antimatter annihilation, there is no waste, no residue. It is the cleanest exchange imaginable, mass becoming energy in its purest sense. Einstein's equation E equals mc finds its perfect embodiment here. A tiny amount of mass yields an enormous burst of energy, because the speed of light squared is such a vast multiplier. This is not just theory. We can see it in practice in laboratories today. When physicists produce antimatter in accelerators and allow it to collide with matter, they witness these flashes of gamma rays, precise and predictable, echoes of the same dance that defined the universe's first moments. The annihilation dance also holds a certain irony. Antimatter is not inherently evil or destructive. It is simply the mirror twin of matter, created alongside it, following the same laws of physics. Yet because of the way our universe developed, whenever it encounters its sibling, the result is destruction. This fate was written not by intention, but by inevitability. In the earliest times, every particle lived under the constant threat of annihilation. Each meeting could mean the end. Each encounter the return to pure light. To survive this dance was no small feat. It meant being one of the rare few to endure, to escape just long enough until the universe cooled, expanded, and became sparse enough to allow matter to persist without constant annihilation. Consider for a moment how delicate this process was. If the numbers had been even slightly different, if the balance between matter and antimatter had been more exact, annihilation would have erased everything. There would have been no atoms to form hydrogen, no stars to ignite nuclear fusion, no galaxies to cluster in spirals and ellipses, no Earth to orbit in the quiet arm of the Milky Way. There would have been only light, streaming endlessly through an empty cosmos. The annihilation dance, in that sense, was a filter, a trial by fire, where only the smallest excess of matter managed to escape obliteration. Even now, annihilation is not entirely a thing of the past. It happens whenever antimatter appears in the universe, fleeting and rare though it may be. High-energy cosmic rays striking Earth's atmosphere can create particles of antimatter, which quickly find their counterparts and vanish in tiny bursts of radiation. In medical imaging, doctors use positrons, the antimatter form of electrons, in PET scans, where their annihilation helps to create images of the body's inner workings. Even in the most advanced particle accelerators, scientists create antimatter for the briefest moments, studying its properties before it inevitably meets matter and is erased in light. Every time this happens, we are reminded that the annihilation dance is not just a story of the past, but a continuing truth of the universe. The balance between matter and antimatter is also central to the mystery of existence. Why was there just enough imbalance to prevent annihilation from wiping the slate clean? Why did a tiny excess of matter escape the dance, lingering long enough to seed the future? The annihilation dance frames the question not only as a physical problem, but as a profound one. The rules allowed for perfect erasure, yet something broke the symmetry. Something tipped the outcome so that annihilation did not have the final word. Without that imbalance, the dance would have ended in silence, and the universe would have remained a stage without players. The beauty of this story is that it reveals the universe not as a place of absolute perfection, but as one shaped by the smallest deviations. Annihilation was meant to erase everything, yet it could not erase all. The survivors of this cosmic dance became the first atoms, the first stars, the first galaxies. They became the foundations of chemistry and biology, the origins of thought and memory, the reason you can close your eyes tonight and imagine these early moments. The annihilation dance was the test, and from its strictness came the fragile possibility of life. To appreciate the mystery of why the universe exists in the form we see today, we must pause and look closely at what scientists call the matter advantage. It was not a grand victory, not a sweeping conquest of matter over antimatter, but rather the smallest of margins, the narrowest escape from total erasure. If the numbers had been even slightly different, we would not be here to tell the story. The universe itself, as we know it, owes its existence to an excess of matter so tiny that it defies intuition, yet so decisive that it became the foundation for everything that followed. This sliver of imbalance is what gave matter its edge, and what ensured that galaxies, stars, planets, and life itself could one day emerge from the chaos of the early cosmos. The birth of the universe. The Big Bang produced matter and antimatter in almost identical amounts. For every particle of matter created, there was a matching antiparticle, a mirror image with opposite charge. The logic of physics seemed to demand that they would cancel each other out, annihilating in brilliant flashes of energy until nothing remained but light. But here is where the story bends. For every billion pairs of particles and antiparticles, there was just one extra particle of matter left behind. 1 in a billion. That tiny, almost imperceptible surplus is what tipped the balance, what gave matter the advantage it needed to persist in a universe that otherwise should have collapsed back into radiation. Without that one survivor in every billion, the cosmos would have been stillborn, a lifeless sea of photons drifting endlessly without structure or meaning. The scale of this advantage is staggering to contemplate. 1 in a billion seems like nothing, a chance so slim that it should have been lost in the noise of creation. And yet, magnified across the unimaginable vastness of the cosmos, that tiny edge became enough. With every annihilation, as matter and antimatter met and vanished into light, that extra particle of matter remained. Over and over again, the dance played out, pairs vanished, energy spread outward, and the lone survivors endured. Slowly, steadily, these survivors accumulated until the universe cooled enough for them to form atoms. First came hydrogen, the simplest of elements, a proton cradling an electron, then helium, forged in the first few minutes of cosmic time. These atoms became the seeds of everything to come, and they existed only because of that slight matter advantage. If we think of the early universe as a game, it was not a fair one. The rules seemed stacked against matter. Every collision threatened its existence. Every interaction with antimatter threatened annihilation. And yet, somehow, matter kept its tiny edge. It did not win by overwhelming force, but by persistence, by that fraction of excess that allowed it to endure long enough to escape total destruction. It is a reminder that sometimes survival is not about strength, but about the smallest of advantages, magnified through time and scale until it reshapes the outcome entirely. This imbalance, known to scientists as baryon asymmetry, one of the great puzzles of modern physics. Why was there an excess of matter at all? Why did the universe favor matter ever so slightly? The laws of physics as we know them seem to treat matter and antimatter symmetrically, as if they should have been produced in equal amounts and destroyed in equal measure. Yet the universe we observe tells a different story. Somewhere in those first moments, the symmetry broke, leaving matter with its narrow edge. That breaking of symmetry is the reason galaxies cluster in the dark, the reason stars shine, the reason Earth spins quietly in its orbit. The universe as we see it is not a product of perfect balance, but of imbalance, a subtle skew in the scales of creation. Consider what this means for the atoms in your body. Every carbon atom, every oxygen atom, every trace of iron or calcium exists only because, billions of years ago, matter had that 1 in a billion advantage. Without it, there would have been no stars to forge heavy elements, no planets to gather them, no chemistry to weave them into molecules of life. That single advantage, multiplied by time and chance, became the architecture of your existence. When you breathe in the night air, when you feel the weight of your body against the earth, you are feeling the triumph of matter's slight edge over antimatter. Every heartbeat, every thought, every dream is part of that long chain of survival that began in the earliest seconds of the universe. The matter advantage also shapes the way scientists look at the cosmos. Every observation of galaxies, every study of cosmic background radiation, is a clue to how this imbalance played out. The faint afterglow of the Big Bang, the microwave background that fills the sky, is a map of those early survivors. It shows us where matter clumped, where it gathered into the first seeds of structure. Without the matter advantage, that map would be blank, featureless, a universe without pattern. Instead, it is rich with variations, with tiny ripples that grew into the cosmic web of galaxies stretching across billions of light years. The matter advantage is not just an abstract concept, it is written into the very shape of the universe we see today. What is perhaps most humbling about this story is how fragile it all seems. Imagine the scales of creation tipped just slightly the other way. If antimatter had been the one with the slight edge, then the universe would have been composed entirely of antimatter, and from that perspective, we would call it matter. To the laws of physics, there is no inherent reason to prefer one over the other. The fact that our reality is made of matter, and not antimatter, is simply the way the imbalance played out. Yet, because of it, our atoms are here, our world is here, and we can wonder about why it happened at all. It makes the question less about inevitability, and more about chance. As if the universe itself leaned ever so slightly in one direction, and, in doing so, set the course for everything that followed. The tiniest advantage became a cascade of consequences. Once matter had that edge, it could combine, it could build, it could evolve into complexity. Hydrogen gathered into stars, stars forged new elements, supernovas spread them across space, planets formed, and life eventually appeared. All of it rests on that razor-thin margin, that 1 in a billion imbalance. It reminds us that the universe is not only vast, but also exquisitely sensitive to its own initial conditions. Small differences in the beginning became the largest differences in the end. The matter advantage is proof of how the cosmos turns the slightest asymmetry into infinite possibility. In the stillness of night, when we look out at the stars, it is worth remembering that each one of them is a survivor, a beacon of matter's advantage. Every light we see is powered by the atoms that endured the annihilation dance, atoms that outnumbered their antimatter twins by only the narrowest of margins. The glow of the Milky Way across the sky is not just the light of stars, it is the light of victory, the triumph of matter's persistence against overwhelming odds. It is the universe's quiet reminder that from the smallest of advantages can come the grandest of outcomes. The universe, as physicists often describe it, is built on patterns of symmetry. Symmetry means balance, fairness, and the idea that nature treats opposites in the same way. If you hold a mirror to an object, and the reflection looks identical, that is symmetry. In the world of particles, symmetry is supposed to mean that matter and antimatter, created as mirror images of one another, should behave in exactly the same fashion under the same laws. It is an elegant concept, one that feels almost too neat, as if reality itself should obey a perfect geometric design. And yet, when scientists began to probe the nature of matter and antimatter more closely, they found cracks in this perfection. Those cracks are what physicists call symmetry breaking, and they may hold the secret to why our universe is made of matter instead of vanishing in a flash of annihilation. In the earliest fractions of a second after the Big Bang, the universe was governed by extreme energies, far higher than anything we can produce today in laboratories. At those energies, the laws of physics looked more symmetrical than they do now. Particles and forces that today seem separate and distinct were unified, and matter and antimatter appeared as though they were equal partners in creation. But as the universe expanded and cooled, the symmetries that once held began to shatter, like ice breaking under strain. These breakages were not catastrophic in the sense of destruction, but transformative, altering how particles interacted and how forces behaved. This is the heart of symmetry breaking, when a system that appears balanced at high energy begins to favor one side over the other as conditions change. For matter and antimatter, this breaking of symmetry seems to have tilted the outcome ever so slightly in matter's favor. If symmetry had held perfectly, then every particle of matter would have had an equal chance of survival as its antimatter twin, and their eventual annihilation would have left nothing but energy. But experiments and theories alike suggest that nature does not treat the two perfectly equally. Somewhere in the deep structure of reality, matter has a tiny edge, a subtle preference built into the laws of physics. This preference is what scientists think may explain why the universe is filled with matter, rather than wiped clean into nothingness. One of the most famous discoveries in this realm came in the mid-20th century, when researchers studying subatomic particles known as kaons observed something strange. These particles and their antimatter counterparts did not behave exactly the same way when they decayed. There was a slight difference, a tiny bias that favored matter. This phenomenon was called CP violation, referring to the breaking of charge parity symmetry, the rule that matter and antimatter should mirror each other when their charges and spatial configurations are swapped. The violation was small, but it was revolutionary, because it proved that the universe does not treat matter and antimatter with perfect equality. This was one of the first direct hints that symmetry breaking might explain why matter survived the early universe while antimatter did not. CP violation is not just a quirk of particle physics. It is a window into the deepest workings of the cosmos. If these tiny differences exist in the behavior of kaons and other particles, then over vast scales of time and energy, they could accumulate into the imbalance we see today. The laws of physics, by breaking symmetry in subtle ways, might have nudged the universe toward matter dominance. It is not that antimatter was erased unfairly, but that the rules guiding its interactions were slightly skewed. Over time, those skews became decisive, leading to the reality we now inhabit. To understand symmetry breaking more intuitively, imagine a ball balanced perfectly at the top of a hill. In theory, the ball could roll in any direction. The system is symmetrical, but in practice, the ball will tip one way or another, breaking the symmetry. That single tipping point determines everything that follows the path of the ball, the direction of its descent, the pattern of its movement. In the case of the universe, symmetry breaking at the fundamental level acted like that tipping point. The laws of physics lean just enough in favor of matter that the outcome of creation was not pure balance, but a cosmos with substance, structure, and life. Another way to view symmetry breaking is to look at how forces themselves have evolved. Physicists believe that at the very beginning, there was a unified force, a single entity from which the four fundamental forces we know today: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force emerged. As the universe cooled, this unified force fractured, separating into distinct interactions. Each fracture represented a form of symmetry breaking, a shift in the rules that allowed complexity to develop. In the same way, the symmetry between matter and antimatter seems to have fractured, favoring one side in the smallest yet most profound way. The search to understand this breaking of symmetry continues today in laboratories around the world. At CERN in Switzerland, at Fermilab in the United States, and at other cutting-edge facilities, physicists recreate conditions that allow them to measure the behavior of particles with extraordinary precision. They study how matter and antimatter counterparts decay, how they interact, and where the differences lie. Each new experiment adds another piece to the puzzle, pointing us toward the subtle imperfections in nature's symmetries. These imperfections may be the very reason galaxies formed, stars ignited, and life arose to ponder its origins. What makes symmetry breaking so compelling is the paradox it presents. On one hand, we expect nature to be fair, to treat opposites equally, to preserve balance. On the other hand, it is the failure of this fairness that gave rise to the world we know. If the universe had been perfectly symmetrical, we would not be here. It is only because symmetry was broken that matter survived, and only because matter survived that stars, planets, and people came into existence. What seems like a flaw in the laws of physics may, in truth, be the foundation of all creation. This realization carries with it a kind of quiet wonder. Symmetry feels beautiful in theory, but it is the breaking of symmetry that made the universe interesting. Perfect symmetry would have meant emptiness, a sterile ocean of light stretching endlessly without form. Broken symmetry meant structure, complexity, and the possibility of life. The very fact that atoms can combine into molecules, that galaxies can spiral across billions of light years, that consciousness can arise to ask questions about the cosmos, all of this is the result of imperfections in the underlying rules. The universe is not a flawless mirror. It is a cracked mirror, and in those cracks lies the spark of existence. When you look up at the stars on a clear night, you are gazing at the consequence of symmetry breaking. Each point of light is a testament to the tiny differences that mattered most. Each star is proof that the laws of physics did not favor balance but leaned, ever so slightly, toward matter. The galaxies scattered across the sky, the planets orbiting within them, the life that thrives on one small world, these are not accidents, but the natural unfolding of a universe in which symmetry was broken at just the right moment. In just the right way. Even now, the mystery is not fully solved. Scientists continue to probe deeper, searching for the ultimate explanation of why symmetry broke the way it did. Was it written into the very beginning? Part of the initial conditions of the Big Bang? Was it the result of hidden particles or forces yet to be discovered? Could neutrinos, those ghostly particles that barely interact with matter, hold the answer? Each possibility points us toward new experiments, new ideas, and new ways of understanding the fabric of reality. Yet no matter how the details unfold, the essence remains the same. Without symmetry breaking, the universe as we know it would not exist. Among all the particles that exist in the universe, neutrinos are perhaps the most elusive, the most ghost-like, and yet they may carry within them the key to the greatest mystery of all. Why matter triumphed over antimatter in the early universe. Neutrinos are so small and so shy that trillions of them pass through your body every second without leaving a trace. They hardly interact with matter at all, slipping through the densest materials as though they were not even there. And yet, despite their ability to go unnoticed, they may have played a decisive role in tipping the balance of creation, giving matter the slight advantage it needed to survive when antimatter did not. To understand the secrets of neutrinos is to peer into one of the quietest yet most profound forces shaping the story of existence. Neutrinos were first proposed in the 1930s to solve a problem in nuclear physics. When scientists studied the process of radioactive decay, they noticed that energy seemed to go missing. A neutron inside the nucleus would transform into a proton and release an electron, but the sums of energy and momentum did not quite add up. Something invisible seemed to be carrying away the missing energy. To account for this, physicist Wolfgang Pauli suggested that another particle must be involved, one with almost no mass, no electric charge, and so little interaction with matter that it would be nearly impossible to detect. This was the birth of the neutrino, a particle so elusive that it would take decades before its existence was confirmed by experiment. Since then, neutrinos have proven to be not only real but also incredibly abundant. They are produced in massive quantities in the nuclear reactions that power stars. including our Sun. They are released in supernova explosions, in the collisions of cosmic rays with Earth's atmosphere, and in the radioactive decay of elements deep within the Earth itself. Even the Big Bang produced a cosmic background of neutrinos, relics from the first seconds of the universe, still drifting through space today. If photons are the messengers of light, then neutrinos are the whispers of creation, faint but pervasive, carrying with them hints of the earliest moments in cosmic history. The connection between neutrinos and the mystery of matter's dominance lies in the possibility that these particles do not behave in a symmetrical way compared to their antimatter counterparts. Just as scientists discovered CP violation in other particles, they suspect that neutrinos may also exhibit differences in behavior that favor matter over antimatter. If this is true, then neutrinos could have been the agents of imbalance in the early universe, tilting the scales ever so slightly in favor of matter. It would mean that these almost invisible particles, so faint they pass through planets without a ripple, are the quiet architects of all existence. One of the most fascinating discoveries about neutrinos came at the turn of the 21st century, when experiments revealed that neutrinos can change their identity as they travel. There are three types of neutrinos, known as flavors: electron neutrinos, muon neutrinos, and tau neutrinos. Scientists discovered that as neutrinos move through space, they oscillate between these flavors, shifting from one form to another. This behavior implies that neutrinos must have mass, however tiny, even though the standard model of particle physics had long assumed they were massless. This was a groundbreaking revelation, one that forced physicists to reconsider the structure of their theories and to admit that neutrinos hold more secrets than previously imagined. The possibility that neutrinos may hold the answer to the matter-antimatter imbalance comes from the idea that they might have exhibited asymmetrical behavior in the early universe. If neutrinos and antineutrinos behaved slightly differently, if one decayed or oscillated in ways the other did not, this difference could have led to an excess of matter. This idea is called leptogenesis, and it proposes that the matter we see today originated from an asymmetry in leptons, the family of particles that includes neutrinos. In this scenario, neutrinos were the subtle agents of change, setting the stage for baryons, the heavier particles like protons and neutrons, to eventually form the visible universe. Experiments are now underway to test these possibilities. Facilities such as Fermilab in the United States and the Japan Proton Accelerator Research Complex are running long baseline neutrino experiments, sending beams of neutrinos across hundreds of miles to underground detectors, in order to study their oscillations in detail. By comparing how neutrinos and antineutrinos behave, scientists hope to detect signs of CP violation, the breaking of symmetry between matter and antimatter in the neutrino world. If they succeed, it would be a monumental step toward understanding why the universe has more matter than antimatter, and why we are here at all. The detectors used to study neutrinos are marvels of scientific engineering. Many are buried deep underground or placed beneath mountains to shield them from other types of radiation. They often consist of vast tanks filled with pure water or liquid argon, surrounded by sensors that can detect the faint flashes of light produced when a rare neutrino does interact with an atom. In some cases, massive volumes of ice or salt are used as the medium, turning natural environments into laboratories for capturing the most elusive of signals. These experiments push the boundaries of human ingenuity, attempting to observe particles that are, by their very nature, nearly invisible. What is remarkable is the sense of scale involved. Neutrinos are so light, so ephemeral, that they seem almost irrelevant in the grand scheme of things. Yet when multiplied across the whole universe, their influence could have been decisive. A particle that can pass through light years of lead without slowing may also be the particle that shaped the very existence of galaxies and stars. In the story of matter's victory over antimatter, neutrinos may have been the quiet voices that tipped the balance, the nearly silent force that decided the outcome of creation. To reflect on neutrinos is to reflect on subtlety. They remind us that not every important thing is obvious, Not every force of creation announces itself with power and brightness. Some forces work in the shadows, whispering instead of shouting, guiding instead of forcing. Neutrinos embody this idea. They are almost nothing, and yet they may be everything, carrying the secret of why the universe is filled with matter rather than swallowed by light. In their quiet, they hold the echo of a choice made in the first seconds of time, a choice that gave us the possibility of stars, planets, and life. In the deep silence of night, when you feel the stillness around you and the vastness above you, it is worth remembering that neutrinos are always there, streaming through you, through the earth, through the sky. They are part of the hidden current of the universe, unseen, yet unceasing. They are the whispers of creation, bearing within them the possibility that without their strange, secretive nature, the universe might have been empty. Every moment, you are touched by their presence, bathed in their flow, a reminder that even the faintest of things can shape the grandest of outcomes. When we talk about the fabric of the universe, symmetry often comes to mind as one of the most elegant and powerful ideas. Symmetry, in the language of physics, represents balance, uniformity, and equality. At the most basic level, a symmetric universe would mean that particles and forces behave in ways that mirror each other, without favoring one side over another. In such a cosmos, matter and antimatter should have been produced in equal amounts during the Big Bang, canceling each other out in a perfect storm of annihilation. Yet here we are in a universe that is anything but annihilated. Stars burn, galaxies rotate, and life contemplates its own existence. This remarkable reality suggests that symmetry, while beautiful in theory, was not absolute. Something broke the balance, and this breaking of symmetry is at the heart of why matter triumphed over antimatter. To grasp the importance of symmetry breaking, imagine the early universe as a perfect, balanced stage. In the first instance after the Big Bang, everything was incredibly hot, dense, and uniform. Physics at this level was ruled by powerful symmetries, uniting forces and particles into elegant relationships. For example, at the highest energies, the electromagnetic force and the weak nuclear force are believed to have been one single entity, perfectly symmetric. But as the universe expanded and cooled, these symmetries began to shatter. The unified forces split apart, particles acquired mass, and new structures began to emerge. This breaking of symmetry was not just incidental, it was essential for creating the rich complexity we see today. One of the most significant examples of symmetry breaking in physics is known as spontaneous symmetry breaking. It is not a violent or chaotic event, but rather a subtle shift, like a pencil perfectly balanced on its tip finally choosing to fall in one direction. Before the fall, all directions are equal. After the fall, one direction is chosen, and symmetry is lost. In the early universe, similar processes took place. The vacuum of space itself, once uniform, selected certain patterns, giving mass to particles through mechanisms like the Higgs field. This act of choosing one state over another broke the pristine symmetry and set the stage for matter to emerge as the dominant presence, the Higgs field, and the particle associated with it. The Higgs boson, discovered in 2012, play a central role in this story. Without the Higgs mechanism, particles like electrons and quarks would remain massless, zipping around at the speed of light, unable to bind into atoms or form the matter we know. It is the Higgs field that slows them down, grants them mass, and allows the building blocks of the universe to take shape. But this granting of mass is itself a product of symmetry breaking, where the universe, in its infancy, selected one stable configuration among many possibilities. In this sense, symmetry breaking is not just an abstract concept. It is the very reason matter exists in tangible form. When we extend this idea to the matter-antimatter imbalance, we find that symmetry breaking again plays a decisive role. The laws of physics, as far as we understand them, should treat matter and antimatter equally. For every particle, there should be an antiparticle with identical mass, but opposite charge. If this symmetry had held perfectly, the Big Bang would have created equal amounts of both, and mutual annihilation would have left behind nothing but pure radiation. The fact that matter survived indicates that symmetry was not perfect, that subtle violations tilted the scales. This is what physicists call CP violation, the breaking of charge parity symmetry. In essence, it means that the laws of physics favored matter in tiny, almost imperceptible ways, enough to ensure that for every billion particles of antimatter, 1,000,000,001 particles of matter were created. That extra sliver, that whisper of imbalance, was all it took to seed the universe of galaxies and stars. CP violation has been observed in the behavior of certain subatomic particles, like kaons and B mesons, where experiments have shown that matter and antimatter counterparts do not decay in exactly the same way. These tiny differences in decay rates are proof that the universe does not hold symmetry sacred. Instead, it allows for exceptions, and those exceptions make all the difference. The breaking of this symmetry may have been rare and subtle, but across the unimaginable energies and quantities of the early universe, it was amplified into a decisive outcome. Matter gained the advantage, and antimatter slipped into near extinction. Symmetry breaking also teaches us something profound about nature's creativity. Perfect symmetry is beautiful, but it is also static, uniform, and featureless. A universe of perfect symmetry would be sterile, without variety or complexity. By breaking symmetry, nature introduces diversity. Forces differentiate, particles acquire mass, and structures emerge. It is in the breaking of symmetry that stars are born, that galaxies take shape, and that life finds a home. In this sense, the imperfection of the universe is its greatest strength. It is the cracks in symmetry that allow for creation to unfold. The concept can even be seen in analogies from everyday life. Consider a snowflake, which forms when water molecules arrange themselves into patterns as they freeze. The laws of physics governing the molecules are symmetric, but when the molecules settle into a solid lattice, the symmetry is broken, producing unique, intricate shapes. No two snowflakes are exactly the same, because symmetry breaking introduces variations. In the same way, the universe's earliest moments contained infinite possibilities. And the breaking of symmetry led to the one unique universe we inhabit. Physicists continue to explore the many ways symmetry breaking shaped the cosmos. Experiments at particle accelerators, such as CERN's Large Hadron Collider, are designed to probe the limits of symmetry, searching for evidence of new kinds of symmetry breaking that could explain why matter prevailed. Theoretical frameworks like supersymmetry extend this quest, proposing hidden partners to known particles, while cosmologists investigate whether symmetry-breaking events in the early universe left imprints in the cosmic microwave background. The afterglow of the Big Bang. Each discovery adds a new brushstroke to the picture of how balance was lost, and how existence was gained at a deeper level. Symmetry breaking also carries philosophical weight. It suggests that the universe, in all its grandeur, owes not from perfect balance, but from imperfection, from the decision of reality to choose one path over another. That choice, whether random, inevitable, or guided by deeper laws we have yet to uncover, was the moment when matter gained its foothold. Without it, there would be no galaxies to observe, no stars to illuminate the night, no planets to harbor life, and no minds to ask why it all happened. Symmetry breaking reminds us that the universe is not a cold, flawless machine, but a dynamic, evolving system where small departures from perfection lead to the richness of everything we know. The story of symmetry breaking is, at its heart, a story of creation born from imbalance. A universe of perfect symmetry would have been silent, uniform, and empty. By breaking symmetry, the universe allowed matter to endure, to clump into stars, to burn in suns, and to rise into consciousness. It is in the broken patterns, the tilted scales, and the subtle imperfections that the true beauty of existence is found. The survival of matter over antimatter is one of the greatest consequences of this principle, a reminder that what seems like a flaw is, in fact, the very foundation of everything we hold dear. When we step back and look at the night sky, we see the result of one of the most decisive events in the history of the cosmos, the survival of matter over antimatter. Without that tiny imbalance, there would be no stars, no planets, and and no life to ask the questions that haunt us today, the universe would have been nothing more than a sea of radiation, sterile and uniform, without structure, without beauty, without purpose. The victory of matter was not just a technical detail in the laws of physics. It was the turning point that allowed the cosmos to blossom into the grand spectacle we witness now. Understanding the consequences of this victory is to understand why there is something rather than nothing, why the universe has a story to tell, and why we are able to tell it at its most fundamental level. The survival of matter meant that the primordial fireball of the Big Bang did not end in annihilation. Instead, after the matter and antimatter pairs cancelled each other out, a small surplus of matter remained, perhaps just one particle for every billion pairs destroyed. This might sound insignificant, a faint whisper against the roar of cosmic energy, but it was enough. Those leftover particles became the seeds of everything that followed. They cooled, they clumped, and they built the foundation of the physical universe. The faint residue of imbalance became the raw material from which galaxies were sculpted. Consider for a moment the scale of what that imbalance produced. The atoms in your body, the iron in your blood, the calcium in your bones, the oxygen you breathe, and the carbon that forms the basis of life, every one of them is made of matter that survived that ancient conflict. The stars that shine in the night sky are nuclear furnaces powered by hydrogen and helium, themselves relics of that surplus. The planets orbiting those stars are sculpted from the heavier elements forged in supernova explosions, themselves only possible because matter endured. Without matter's triumph, the universe would be a vast desert of light, with no structures to punctuate its emptiness. The consequences stretch far beyond individual atoms. Matter's victory gave rise to gravitational clumping, the process by which tiny fluctuations in density grew into galaxies and clusters. In a universe without matter, gravity would have had nothing to work on, no particles to gather, no seeds of complexity to amplify. The cosmic web, the grand lattice of filaments connecting galaxies across billions of light years, exists only because there was matter to weave it. That same web is the scaffold upon which the large-scale universe rests, a reminder that all of cosmic architecture was built upon the faintest imbalance in the earliest seconds of time. One of the most profound consequences of matter's survival is the existence of time as we perceive it. A universe of pure radiation would have expanded and cooled, but without the formation of structures, there would be no milestones, no markers of change. It would be timeless in a sense, a monotony of light without history. Matter introduces narrative. With matter, there are galaxies that evolve, stars that are born and die, and planets that circle their suns in rhythms we call years. With matter, there is change, and with change comes the possibility of memory, history, a future. The arrow of time, as we understand it, is written in the story of matter's endurance. The victory of matter also made possible the chemistry of life. Atoms combine into molecules, molecules into complex chains, and eventually into the biochemistry that sustains organisms. This layering of complexity depends entirely on the fact that particles like protons and electrons are stable and available, not obliterated in the first instant of creation. Imagine a universe where that imbalance never occurred. The very laws of chemistry would be irrelevant, because there would be no atoms to bond, no molecules to form, no DNA to encode life. The fact that we can think, feel, and wonder about the cosmos is itself a consequence of matter's improbable survival. It also gave rise to diversity, not just the diversity of particles and forces, but the diversity of worlds. Stars do not simply shine. They evolve, they create heavy elements, and they scatter them across the cosmos in cataclysmic bursts. Planets form in the debris of these events, each unique, each a product of chance and circumstance. Some worlds become barren deserts, others frozen wastelands, and some, like Earth, emerge as cradles for life. All of this richness traces back to the tiny surplus of matter that escaped annihilation. From that surplus grew the possibility of landscapes, oceans, forests, mountains, and the infinite variations that make the cosmos not just habitable but beautiful. The consequences can even be felt in the way we experience awe. The night sky is not just a black canvas dotted with stars. It is a window into the cosmic victory of matter. Each star is a survivor of that imbalance. Each galaxy a monument to asymmetry. When you look at the Milky Way stretching across the heavens, you are witnessing the grand consequence of a moment in time when the universe chose matter over antimatter. The very act of stargazing, of contemplating existence, is only possible because the universe leaned ever so slightly in favor of matter. From a scientific perspective, this victory continues to shape our understanding of physics. Every attempt to model the early universe must account for the fact that matter exists in such abundance compared to antimatter. The standard model of particle physics, while remarkably successful, does not yet fully explain this imbalance. This drives scientists to push deeper, to design new experiments, to search for new particles, and to explore ideas that extend beyond the current framework. The very fact that the universe is made of matter remains one of the most compelling motivations in the pursuit of fundamental physics. It is not just a question of curiosity, it is a question of identity, of why the universe looks the way it does, and why we exist to see it. There are also philosophical consequences. The survival of matter reminds us that the universe is not governed by perfect symmetry or flawless balance. It thrives on imperfection, on the breaking of symmetry, on the small deviations that allow creation to unfold. This can be a humbling lesson. What we see as imbalance or flaw may, at a deeper level, be the very thing that makes existence possible. In a sense, the universe teaches us that perfection is sterile, while asymmetry gives rise to life. The victory of matter over antimatter also resonates with the human spirit, because it mirrors our own struggles. Just as matter endured against overwhelming odds, so too do we find meaning in endurance, in survival, in persistence. The cosmos is a story of resilience, of a fragile surplus that became a universe, of imbalance that became beauty. To recognize this is to feel connected to the very roots of existence, to see our own survival as part of a much larger narrative. Perhaps the greatest consequence of matter's survival is that it gave the universe the capacity to know itself. Through billions of years of evolution, matter assembled into stars, into planets, into organisms, and eventually into conscious beings who could look back and ask why. This capacity for reflection, for wonder, for science, is the final triumph of matter's victory. Antimatter may have vanished, but matter gained the ability to dream, to question, to imagine. In that sense, the survival of matter is not just a physical fact, it is the origin of meaning itself. Even though modern science has made incredible progress in understanding why the universe is filled with matter rather than antimatter, the story is still unfinished. The great cosmic imbalance remains one of the most profound puzzles of existence. Physicists can describe in exquisite detail how particles interact, how stars shine, and how galaxies evolve. But when it comes to the question of why matter won the primordial battle, the explanations are still incomplete. We are left with theories, glimpses of possibilities, and the promise of experiments that might one day reveal the truth. This keynote explores those unanswered mysteries and looks forward to the discoveries that may lie ahead. Discoveries that could reshape our understanding of the cosmos and our place within it. One of the deepest mysteries is simply why the imbalance occurred in the first place. We know that matter and antimatter annihilate upon meeting, and we know that equal amounts should have been produced in the Big Bang. The fact that matter survived implies that the universe had built-in rules that favored it, but what those rules are remains elusive. The standard model of particle physics allows for small amounts of CP violation, meaning that the laws of physics can treat matter and antimatter slightly differently. But the amount predicted is far too small to account for the overwhelming dominance of matter in the cosmos. This discrepancy suggests that there are forces, particles, or interactions beyond the standard model waiting to be discovered. Some theories propose that heavy particles existing only in the earliest moments of the universe may have decayed in ways that favored matter over antimatter. These hypothetical particles, far too massive to be produced by today's accelerators, could have set the imbalance into motion through processes known as baryogenesis or leptogenesis. Baryogenesis focuses on mechanisms that directly produced an excess of baryons, the family of particles that includes protons and neutrons. Leptogenesis, on the other hand, suggests that the imbalance began with leptons, the lighter family that includes electrons and neutrinos, and that this asymmetry later translated into the matter we see today. These ideas remain tantalizing but unproven, and testing them requires both experimental ingenuity and theoretical creativity. Neutrinos, in particular, continue to capture scientific attention. These ghost-like particles, which barely interact with the rest of the universe, may hold clues to the asymmetry. If neutrinos and antineutrinos behave differently, especially in the way they oscillate between flavors, they could provide the missing piece of the puzzle. Major experiments, such as the Deep Underground Neutrino Experiment DUNE in the United States and the Hyper-Kamiokande project in Japan, are being designed to probe these behaviors with unprecedented precision. The results could reveal whether neutrinos are the key to explaining matter's victory and whether they carry, within them, the record of a universe tilted in favor of survival. Another great mystery lies in the possibility of hidden symmetries or undiscovered particles. Supersymmetry, for example, is a theoretical framework that extends the Standard Model by proposing that every known particle has a heavier superpartner. These superpartners, if they exist, could have played a role in shaping the matter-antimatter imbalance. They might also help explain dark matter, the invisible substance that makes up most of the mass of the universe. If supersymmetry is confirmed, it would be a revolutionary step toward unifying the forces of physics and understanding why the universe is the way it is. Yet so far, searches at particle accelerators like the Large Hadron Collider have not found definitive evidence, leaving the question open and the mystery alive. Cosmologists also look to the earliest moments of the universe for answers. During the first fractions of a second after the Big Bang, the cosmos underwent rapid inflation, expanding faster than the speed of light. This inflationary period may have amplified tiny fluctuations and influenced how matter and antimatter interacted. The afterglow of the Big Bang, known as the cosmic microwave background, carries subtle imprints of these processes, and scientists study it with extraordinary precision to extract information about the first moments of time. Future missions and observatories may detect signatures of symmetry breaking or anomalies that point toward the origins of matter's dominance. But the mysteries are not only about the past, they are also about the future. If the imbalance that created our universe was born from subtle asymmetries in the laws of physics, then those asymmetries continue to operate today. Do they hold implications for the fate of the cosmos? Will they help determine whether the universe expands forever, collapses back on itself, or reaches some new phase of existence? Could they reveal connections between the known universe and hidden realms of reality, perhaps even multiple universes with different balances of matter and antimatter? These are not just questions for scientists. They are questions that touch on the deepest philosophical reflections about why anything exists at all. What makes this quest especially profound is that it blends the smallest scales with the largest. To understand why galaxies exist, we must study the tiniest particles. To grasp the origins of stars, we must unravel the behavior of neutrinos. To answer why we are here, we must ask how symmetry was broken in the first microseconds of time. It is a reminder that the cosmos is deeply interconnected, that the smallest details ripple outward to shape the largest structures, and that our search for answers requires us to look both inward and outward, into the subatomic world and into the depths of the universe. What is clear is that the story is not finished. The experiments of today may uncover tomorrow's revelations. The unanswered mysteries of matter and antimatter are not failures of knowledge, but frontiers of discovery. They remind us that the universe is vast not only in size but in depth, that its secrets are layered, waiting to be uncovered one by one. And as long as we continue to look upward and inward, as long as we continue to ask, why? We remain part of the same story that began with the faint surplus of matter, a story still unfolding in the great expanse of time and space. As we reflect on this grand journey through the mystery of why the universe chose matter over antimatter, we return to the realization that our very existence hinges on the faintest imbalance written into the laws of physics. In the first breath of creation, matter and antimatter emerged as twins, destined to annihilate, yet in that cosmic dance, a subtle asymmetry tipped the scales. Out of every billion pairs, one particle of matter remained, and from that fragile surplus arose everything: the stars that illuminate the night, the galaxies that stretch across the cosmic web, the planets that cradle oceans and mountains, and the life that breathes, thinks, and wonders. The story of this imbalance is not one of perfection, but of broken symmetry, of subtle departures from balance that allowed the universe to grow complex, diverse, and alive. Neutrinos may whisper the hidden truths of creation. CP violation may reveal the preference of nature for matter, and the Higgs field may stand as the silent sculptor of mass. But even now, the full picture eludes us. The unanswered mysteries remain vast, and yet, it is in those mysteries that discovery thrives, pushing us to build deeper theories, more sensitive instruments, and broader visions of reality. What is most humbling is that this question, why matter triumphed over antimatter, is not abstract. It is personal. The atoms that make up our bodies are survivors of that ancient imbalance, each one a relic of the universe's earliest decision. We are living evidence of matter's victory, consciousness born from asymmetry, awareness shaped by imperfection. The universe did not choose balance. It chose survival. It chose creation. It chose story. And because of that choice, we are here, able to look into the night sky and ask why, able to dream of answers, and able to find wonder in the fragile beauty of existence.